Good morning, everyone. My name is Bertrand Irisu. I'm the CEO and co-founder of Brainome. It's my pleasure to welcome you to our first webinar on the benefits and applications of our measurement-based approach to machine learning. Our topic today is supercharging your data prep, and will be presented by Lynn Chase. Lynn is our VP of Product Management at Brainome, which means that she's laser focused on making our Daimensions users successful. She earned her PhD in computer science at Carnegie Mellon in 1997 and has been working on making AI software useful in the real world since then. She joined Brainome a few months ago, bringing with her an extensive multi-decade track record of very successful development and deployment of AI technology in complex business environments. So for seminars, we currently have two concurrent seminar series going on. One is called Core Tech, which is actually much more technical in nature and goes over a lot of the math behind our measurement techniques that we use in our software. And this is the first of the benefits and application track. These are weekly seminars, and we encourage you to sign up for them at www.brainome.ai/resources/events. If you have any question, please put them in the Q&A channel, and then we will answer them at the end of the webinar. And so without further ado, Lynn. You're muted. There we go.
Hey, everyone. Glad to see you. Thanks for joining us today. I would like to start by asking a basic question, which is that as a machine learning practitioner or a data scientist, when you're at the beginning of trying to work on a problem, do you have a way of saying or projecting or predicting how much money, CPU, memory IO, staff time, you're going to need to budget to do the deep learning work? And the answer is, with the tools that are available in the industry until Brainome came onto the scene, the answer was no. There's no answer to that. There is, however, a culture and a set of practices that are quite commonly held that more is always better, whether that's using more data or getting your hands on more compute or building a model with more parameters. That's what everybody thinks is the right way to go. This leads to something that quite commonly happens, which is that you can spend months and months gathering and labeling data and getting your data ready for training and validation. And then you can spend weeks training models, and in the end up with a kind of a meddling result, a meh result, 73 or 82% or 81% accuracy on some validation set, which is not really what you were hoping for, but you don't have any way to figure out what to do next to improve the situation. The most common reaction is to try to add more data, to try to get more data built into the process to try to improve performance. Because really, you have no way of knowing what to do. You have no way to measure what to do. You have no way to get the insight into what you need to do in order to improve. What I'd like to show you today is how Brainome's solution, which is the first, measure before you build approach to doing supervised machine learning, how, by measuring the learnability of data against different types of potential machine learning models, doing that in advance before you build gives you a superb advantage, especially when you're doing data preparation. And that's what we're here to talk about today. We're here to show you how you can know when you have enough data, how you can know when you have the right data features, how you can know whether or not you're going to overfit, given the data that you have and the particular type of model that you're trying to build, how to know which type of machine learning model will work best with your data, how long it will take you to train that model, and to know in advance which of your data features are actually impactful with respect to prediction. There's also something here that's grayed out at the bottom, which is a post-build measure that we can help you with, which is using those same measurement kits after you've built measurement tools, after you've built a model, to know which of your data labels are most reliable. in your classification scheme. So let's take a look one by one at what each of these measures are and how they look in the software, how they look in the Daimensions software. First, you can upload your data. And what we've got here is a couple of screenshots from the GUI version of our software, which is available for free on our website. You can go and just try a demo, or you can give us your email address and become a registered account and get a slightly more spiffed up, more advanced version of the software. And that's what the GUI interface looks like. But for enterprise customers who are paying customers, we also have a superpowered command line interface version of the software. And what you see down here is what the command line version of the software looks like when you're interacting with it as a power user. So anyway, we start with uploading a data set. In this case, we're uploading a preset test data set that's available on the website, but you can also upload your own data to give the software a whirl. And then you just click the measure button. Or if you're running the CLI version, you run the Daimensions software, you give it a CSV file that's got all the data in it as an argument, and you put on the measure only flag. So that's how you kick things off. What comes out initially is some very basic stuff that really any tool on the market will give you a sense of what the class balance is. That is how balanced are the labels in your target column that you're trying to predict. In this case, we've got a binary situation where we've got two classes that we're choosing between in the predictor. And it tells you how many rows there are, how many instances or samples there are in the data set that you're looking at, and how many attributes or columns. And this is what it looks like on the GUI interface, and this is what it looks like in the command line interface. Again, very basic stuff, nothing new here, but definitely necessary as a foundation for going forward. Here's where we get into where Daimensions is different. I want to stop and do a kind of a high-level description of something we call capacity progression. This is core to what's different, what's the secret sauce in the Brainome Daimensions software. So first of all, I want to introduce the notion of model complexity. Model complexity is the number of decision points needed to capture the rules or the patterns that are present in the data that you're using for training and validation. And it is measured against the type of model. In this case, we can tell you against either a decision tree or a neural network. Those are the two types of machine learning models that we're currently able to calculate model complexity on. The number of decision points in a decision tree is directly related to the number of split points in the decision tree, the number of decision splits that happen. And the number of decision points in a neural network is directly related to the number of neurons in the internal layers of the neural network. So we have a way of measuring, before building a model, what the upper bound is, what the maximum number is for the model complexity for either a decision tree or a neural network. And what we're interested in looking at in order to make a first step towards measuring learnability of the data that you've given us, is we start by looking at the first 10% of the data just randomly sampled. And we measure the model complexity on that first 10%. And then we add another 10% and we remeasure the model complexity, and we continue to 30, 40, 50. And what we would like to see, if the data is in fact learnable, if it is in fact to extract general rules from the data as being presented, is that this model complexity, this capacity progression, will level off and will plateau or converge as we increase the percentage of the data that we're looking at. If, however, that doesn't happen and you see a complete linear relationship, continued growth in the model complexity as you continue to look at more and more of the data, then we're in a situation where the data does not have learnability. And that's a very important thing that we can measure that no one else can. So for instance, this is just a super, super simple example. If you're looking at data that is a sequence of numbers like 2, 4, 6, 8, 10, 12, etc., the capacity progression will plateau, it will converge, it will level off, because this is very much a learnable rule, and that data is very learnable. Whereas if you're just looking at a completely random sequence of numbers coming in 6, 5, 1, 3, blah, 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 there's no pattern there. If you continue to look at more and more data, the model complexity is going to continue to rise linearly, and therefore we would conclude this is not a learnable situation. So that's the fundamental idea of what we're measuring, kind of presented at an abstract level. Here's what it looks like in the software. In the GUI interface, you're going to see a graph that looks like this. It's going to be percent of total data. And you'll note here that this is no longer linear. It's actually logarithmic down on the bottom. But the number of decision points is the same. And what we're seeing here is, in this case, it's pretty much plateauing. It's not a perfect plateau. We do see a kind of a rise here in the 40, 60, 80 region. But it's not an absolute, an absolute linear progression upwards either. So this is a situation where we would say not red, not horrible, not a stop, but not a total slam dunk green either. This is a yellow situation, just like the stoplight, red, green, yellow. So this is very common actually to see some plateauing, but not perfect. So we need to look at other measures as well, which we'll get to in a second. This is what the capacity progression output looks like when you're using the Power User command line interface version of the enterprise product as well. So that's what it looks like in the GUI. That's what it would look like if you're using it at the command line. Now, in addition, we can give you a direct count of the number of parameters, the upper bound, the maximum number of parameters that would be needed if you were going to build a model that was either a decision tree or a neural network. And in this case, on the data that we're looking at in this example, the decision tree upper bound would be 391 parameters, and the neural net would be 199 parameters. Parameters in a decision tree are directly correlated with how many decision points there are. There's basically one parameter per split. In a neural network, however, a perceptron, because it has a bias and 2 weights on the inbound links, each neuron actually is 3 parameters on average. So we're going to actually measure the total number of parameters in the neural network here, not just the decision points. So we see the parameter count in a graphical representation, and on the command line, this is what the printout looks like. We also have a measure called generalization. Generalization is a measure of, it's a direct measure of learnability of the data. And it essentially tells you if you start with all the data in a training set and you find rules that allow generalizations to occur in the predictions, what kind of compression can you get? How much can you reduce the total amount of memory needed to capture what the rules are that you're actually going to generate in the predictor? So a generalization ratio that's higher is better, because that means you can actually compress from a starting point with all the data that you have to something that's smaller in order to get generalized predictions out of the learned predictor. So generalization ratio here looks like it's better for the neural network, and it's good, but not quite as strong for the decision tree. If you're interested in the details of what generalization is and how exactly it's calculated and what exactly it means, I highly encourage you to go see our Core Tech series, Core Tech 101, 201, and 301, where Gerald Friedlands, who's our CTO, will take you through all the math and all the algorithms of what's going on there. I just gave you a very high level description here. So if you're at all frustrated by that, definitely go see the Core Tech presentations to get more detail. Another measure that we can tell you is how close are you to potentially having to overfit in order to get good accuracy out of your model. And again, if you want the exact details of this, go watch the Core Tech seminar series. But what I can tell you as an interpretive rule here is, if you're in the GUI interface and your arrow on overfit risk is anywhere in this red region, then you're in trouble. Your data is not sufficient to provide avoidance of overfit. But if you're in the yellow or the green area, you should be okay. The way that this looks on the command line is these percentages are actually just printed out. And so the interpretive rule there would be, if you're in the high 90%, you're in trouble. Otherwise, you should probably be okay. Again, if you want the details on that, Cortex seminar is where to go. Overall, we'll give you a recommendation of whether or not you have enough data to generalize properly. And on the command line interface, we'll actually give you the red, green, yellow indication as well. In the GUI interface, you get this recommendation and it's just printed out for you to read. In the command line, you'll also get at the same time a notion of which type of machine learning model you should go with. In the GUI interface, we actually just pre-select for you the recommended type of model to build, and then give you the option to push the build button. In both cases, in both the GUI and in the command line, we'll give you an estimate of how long that build time would take. And this is another invaluable feature of the ability to measure before you actually build anything. So how does this all play out with respect to doing your data preparation, your data prep? The point is that with the measurement, you can situate yourself in a feedback loop where you can configure your data. You can pick an amount of data and what type of features, and you can say, okay, given that this is what I'm thinking of as my training and validation data, give me the measurements so that I can see whether I'm on the right track. And then you can iterate very rapidly. The iterations can take less than a minute. So this is the place where you gain an enormous amount of information and you do it very, very rapidly. Let's take a look at what it means to configure data options before you measure. Let's look at a couple of examples. One of the very basic things we can do to configure data is to pick how much data we're going to try to train on. So here's an example of a data set that had 279 attributes. It was a binary classification problem, and it had pretty good class balance. It was roughly close to 50-50, probably 55-45 if I recall. So we started with just a very small amount of data, and we ran the measurements, and the recommendation came back as red. The capacity progression was not even able to print out because there was too little data. Generalization was pretty low, and the risk of overfit was very, very high. So we doubled the amount of data. We went and collected and labeled another twice as much data. We were still red, data set was still too small. Generalization hadn't really changed much. Risk of overfit was very, very high. Okay, so then we doubled down and we went from 100 rows, 100 samples to 250. Finally, we broke through where we had enough data to at least measure the capacity progression. And we got maybe it's okay, we're in the yellow zone now, but the risk of overfit was still super high. So not comfortable yet. So add some more data incrementally. Capacity progression still looks pretty good. Generalization is starting to look better. Risk of overfit also looking better. Let's just do a little more to see if that continues. We're still good. We were in the yellow zone. Capacity progression looks the same. Generalization is improving. And the risk of overfit is now well down into the safe zone. So that's where we stopped. We found that with 452 samples, we had enough data and it was going to be learnable. So that's a great example of something very basic you can do to configure data options and then go through an iterative measurement and feedback loop. And it's a great way to not overspend on the data that you're gathering and labeling while you're building up a new project or a new predictor or a new problem solution. So that's incrementing number of rows. That's one thing you can do. Another very, very powerful thing you can do is rank or remove columns, meaning you can ask the software to tell you which of the columns, which of the data features in the data set that you're working with actually have an important impact on the outcome of the prediction you're trying to make. So this is solving another major problem in data prep, which is feature design, data feature design. It gives you a way to iterate very, very rapidly and to figure out which of the data columns are actually going to be worth collecting and worth spending the time doing labeling on. In the GUI interface, it's really easy to do. You just automatically get a feedback from the system on which of the data features in your data set are causing any kind of impact. And there's also an active selection, an active suggestion of which of those data features are the ones you should really be focusing on. And then in the GUI, you can select and unselect and go with the suggestion of the system or add your own. And you can do a very rapid iteration on experimentation on which features are selected. And the same kind of feedback in the command line argument gets printed out, but you just have to read it as text. In the command line argument, you also have a minus rank option that you can use as a flag, and you can actually choose which columns to ignore using a minus ignore columns flag as well. So you have full control in the command line version, just like you do in the GUI version. So that's another way where, by picking and choosing which data features are included in the measurements, you can very rapidly figure out what your data feature set should be. And that's a huge time saver and a huge insight bringer for machine learning experts. There is one quick post-build option I wanted to run through just in case you find it interesting. This is not something we can do prior to measurement. You actually do have to go through building a model, but building models, especially decision trees using our software, is also extremely fast. So the same rapid iteration is available to you even for this kind of measurement, which is you can remove or combine rows in order to, you can remove or combine or you can remove labels or combine rows in order to figure out which of the data labels that your data has been labeled with are reliable and which aren't. So that's not a problem everyone has. Some domains it's more important than in others, but I just wanted to mention that in addition to figuring out which data features can be powerful for you and which ones should be eliminated, you can also do the same thing with your data labels for your classification. I just wanted to give you a word from one of our customers, Eric Davis at SK Telecom. They've been able to really, really rapidly improve the quality and the speed at which they're doing data preparation. And they've been able to take their problem solving efforts with machine learning from weeks or even months of effort down to just very, very short periods of time. So I just wanted to put that word of confidence in there for you to see. The bottom line is that we've created and are now delivering the first systematic engineered measurement-based approach to doing supervised machine learning. And we're very excited about that. And we would like you to try it out. I think I can pass this back to Bertrand now.
Great. Thank you, Link, for this great presentation. If you have any questions, please put them in the Q&A. I actually have a couple that came through the chat that works too, to the panelists. So let me start with the first one coming from Sean. Sean says, I don't really understand what you mean by generalization or why it's one of your measurements that helps to guide data preparation. Can you maybe explain that again, Lynn, or
Sure, yeah, absolutely. Again, I'll just do it at a conceptual level, and I'll invite you to attend the core tech seminars to actually see the math and have Gerald explain it to you. But the basic idea is this. If you start with your training data and it's got some number of rows and columns, it's going to be the most amount of space that you need in order to capture all the information that's in that data set. But if we can find rules, if we can extract rules that describe what's going on in that data, if your data is learnable according to the measures that I was just talking about, the total amount of space that you need in order to capture what's going on in that data set gets smaller and smaller. And generalization is a direct measurement of essentially how much compression, how much smaller and smaller can happen as you extract rules from the data and create a predictor. Is that helpful?
Well, I can't see anybody nod, but I'm gonna hope it is.
Great.
Okay, we get a second question from Jordan is asking saying that data prep is actually a major unpredictable cost for him. Can this really help him, and if so, how?
Well, I would really love to talk to you. It was Jordan, was it? I didn't quite catch the name. I'd love to talk to you, Jordan, about that. The thing that most people find useful is one of two things. One is that you can, instead of upfront trying to guess how much labeled data you're going to need, you can actually take an incremental approach and invest incrementally in the gathering and labeling of data. Or you could gather all the data, but only incrementally invest in the labeling, which is the expensive part. Typically, people have to get 2 separate labelers to work on a data set, and then they have to worry about interoperator agreement between those labelers, and that can be very expensive and time consuming. So what we're able to do is we're able to say, using this rapid iteration approach, try a little bit, see if you have enough, try labeling more, and when you have enough, when we tell you that your data is now learnable and that it's workable, then you have enough. And that's a way to really take a lot of cost out. You don't have to guess ahead of time how much of your data you need to spend on that sort of expensive and manual labeling process. So that's one place where people save a lot of money. The other thing that people find very useful is just the question of the design of the data set itself. What data features are actually needed in order to create the predictions and the outcomes that are desired? And we give a very direct way to measure and a very rapid means of iterating through data feature design. And so that's the other place where people save a lot of headache and a lot of time and money as well. So, but I would love to talk with you personally about your situation, just to make sure that those things are applicable.
Great. I see one last question came from Linda. This is my data sets typically have over 500,000 data rows. How quickly can you actually compute capacity progression compared to, say, building a model?
Yeah, it 500,000 is well within the range of what we would often see. I'd be curious how many columns you also have, but I'm going to assume that it's sort of on the order of a couple hundred. So something that's a couple hundred wide and a million long, we should be able to iterate within minutes on making those measurements. Now, building a model on that much data is also going to be fast for decision trees, but it might take a while. It might go up to order of an hour or more for building a neural network, depending on what you ended up needing.
Great, thank you. Don't have any more questions at this point.
Okay.
I see there was a couple people who came in a little late and might have missed a part of the talk here. I want to remind everyone that we will have actually a recording of this presentation shortly available on our website, so feel free to go back and take a look at it. I'd like to remind you again that we have 5 more seminars in this series, and the next one will be Find a Needle in a Haystack, which is about basically working with a very large number of features, thousands and more features, and not necessarily a whole lot of data available, and building meaningful model with Daimensions. We also have a parallel series of webinars which are more technically oriented, which are the Cortex series. There's also weekly seminars, all happening next week. So please go to brainome.ai resources event to sign up and learn more about our technology and how it can help you in your machine learning development process. I also encourage you, if you haven't done so, to go on our website and try our demo. We have a demo you can try without signing up, but you can also register and get more a little more capability out of the tool. And of course, if you are interested in the tool professionally, we encourage you to contact us directly. You can email support@brainome.ai or contact our sales office as well, and we'll be very happy to work with you a real pilot for with our product. Thank you again for attending, and hopefully see you all next week.